Let me introduce François Hamel from Université Aix-Marseille. So he will talk about radial symmetry for the Euler equations and semilinear elliptic equations. Thank you.
Okay, thank you very much, Benedetta. And let me also thank to Alberto, you, Benedetta, and Francesca for the kind invitation and for organizing this event, despite of the difficult global situation. So I'm very happy to see you and also to see the other people of the conference, some of whom I have not seen for a long time. So the talk is based on some joint works with Nikolai Nadirashvili. So I'm sorry for some of you who have already heard some parts of the talks, but I thought that it is well fitted with this conference because I'm going to use some ODEs arguments to study some PDEs. So, and the talk is on radial symmetry for the Euler equations and semilinear elliptic equations. So, I will focus on the steady Euler equations for an inviscid incompressible fluid. So these equations are first order equations for the flow V. So the flow V is a vector field assumed to be divergence free, and there is a pressure in the equation. And this equation is set in a domain omega. So once again, it is a steady equation. So the fields only depend on the spatial variable. And we assume that the flow V is of class C2 of omega bar, which is more than the usual regularity because we only have a first order equation here. But this assumption plays a role somewhere. You will see that later in the proof. Maybe we can relax it to C11, but the arguments as such cannot get rid of this type of assumption, despite of the fact that the results may still be true without this assumption, but this would require another proof. So the question is, the basic question I'm going to address today is the following. How does the flow inherit the geometry of the domain? So we are given a domain omega, and we want to see what type of geometric properties the flow inherit from the domain. And today I will focus on circular domains. And the question is, so in a circular domain, can one find conditions for a flow to be a circular flow? And I will discuss some sufficient conditions in dimension 2. So in dimension 2, a circular domain is an annulus. So I will discuss several types of annulus, of annuli. So the regular annuli and also the exterior of a disk, and also a punctured disk, and also the punctured plane, and also at the end, if I have time, the whole plane R2. So so let me first focus on the case of a regular annulus, so which is a domain in the plane between two concentric circles of radius A and B. So A and B are fixed. So positive real number. And omega AB is this domain. And let me denote ER, the radial vector field, and E theta, the perpendicular vector field. So at a point, so ER is like that, and E theta is like that, okay? So at each point X. And okay, so let us consider, so the first result is the following. We consider flow V in this domain, in this regular annulus. And let us assume that it satisfies tangential boundary conditions. So the flow is tangential on the two connected components of the boundary of the domain. So this condition refers to the rigid wall condition. So, and we also assume that the flow has no stagnation point in the closed annulus. So no stagnation point. And then the conclusion is that the flow is a circular flow, which means that at each point x, the flow is parallel to the vector E theta with a magnitude which only depends on the norm of x because of the incompressibility condition. And this, so this magnitude is a function capital V of the norm of x, and of course, capital V does not vanish by assumption. So, so this result gives a sufficient condition for a flow to be a circular flow. So what does the conclusion mean? The conclusion means that the streamlines of the flow are concentric cycles. So the streamlines are curves parameterized by this family of ordinary differential equations, which are the trajectories of the flow. So for each x, there is a streamline, and Cx, which is parameterized by this equation. So Cx satisfies an ODE, this ODE. Okay, and so the streamlines are all concentric cycles. So an equivalent formulation of the statement is that any non-circular flow tangential on the boundary must have at least one stagnation point in the closed annulus. Okay, and it is we can actually relax a little bit the assumption of no stagnation point by assuming that the set of stagnation points is properly included into one of the connected components of the boundary. So what I mean by properly included is that it is included and not equal to. So, but with this assumption, the conclusion is that the flow has no stagnation point anywhere, because the conclusion is that the flow is a circular flow, and therefore the function capital V does not vanish anywhere in the closed interval AB. So let us assume for simplicity that the flow has no stagnation point in the closed annulus. Okay, so we get we have this result. And let me comment it a little bit by first saying that so without takes time for the page to be seen. So without this assumption, the conclusion does not hold in general. So it's quite easy actually to find counterexamples. So for instance, if we consider any classical solution U of such an equation, semilinear elliptic equation in the annulus, with a function f which is at least of class C1, of class C1. It's at least Lipschitz continuous, but let us assume of class C1, and assume that U is constant on each connected component of the boundary. So U is constant on the cycle of radius A and on the cycle of radius B, but the constant, the values can be different. Then if we introduce this flow, so the orthogonal gradient of the flow, so here we have gradient of U, and the orthogonal gradient of U is this vector field, so we rotate with an angle of pi/2 counterclockwise. So this vector field V obeys the Euler equations. So this is because of the fact that U satisfies this semilinear elliptic equation. And the flow V is associated to pressure P, which is explicitly given by this formula. So, okay, so therefore it's quite easy to construct in such a way. It's well known to construct a well-known fact. Okay, so So now, if we say that if we assume that U has critical points in the domain, then V has stagnation points, because the critical points of U are the points where the gradient vanishes, so which are the stagnation points of the flow. And also, if U is not radial, then V is not a circular flow. So, okay, so based on this well-known fact, we can consider let us consider, for instance, this eigenvalue problem. So this eigenvalue problem in the interval AB with Dirichlet boundary condition. So we consider this operator. So this operator here, so second order operator with coefficients which depend on R in the interval AB. So it has a principal eigenvalue lambda associated with a principal eigenfunction phi, which is unique up to multiplication. So, and which is characterized by the fact that it has a sign. So positive, let's say, up to multiplication. So and with Dirichlet boundary condition. So, but what is this? Operator? It is just the it corresponds to the Laplace equation for. So the first two terms correspond to the Laplace equation for a regularly symmetric function, and then because of this additional r minus 2 coefficient, we can say that the function u of x, which is phi of r times cosine theta within the polar coordinates. So this function u solves this semilinear, which is actually linear equation. So this eigenvalue problem, Laplace u plus lambda u is equal to 0. So the cosine theta is involved in this coefficient r minus 2 times phi. So it is cooked up in such a way that u satisfies this equation. And this function, it is quite easy to see that the function u has 6 critical points, 2 on the inner boundary, 2 on the outer boundary, and 2 in the interior annulus. And the flow V is not a circular flow, so with 6 stagnation points. And this flow, so okay. So it's just a counterexample. So when the flow has a stagnation point, so the conclusion does not hold in general. Okay. And but I also would like to point out that the condition of absence of stagnation point is obviously not equivalent to being a circular flow. It's just a sufficient condition, but not equivalent, because there are circular flows with stagnation points besides the trivial flow. So for instance, just simply consider this, once again, this eigenvalue problem, but now just the first two terms, which correspond to the Laplace operator for regularly symmetric functions. So we consider this operator. It has a principal eigenvalue mu, principal eigenfunction phi, with the Dirichlet boundary conditions. And so the radial function u of x given by phi of r with radial coordinates satisfies this linear equation, and the set of critical points is equal to a cycle, some cycle with a radius r star, which is strictly between a and b. So r star corresponds to the unique critical point of the function phi. So this flow V is a circular flow with infinitely many stagnation points. Okay. So I would like to now to spend maybe at least 5 minutes to give you some ideas of the proof, because the proof is quite simple to understand here in this situation. And I would like to make the connection between the ODE arguments and the PDE arguments. So we consider so the stream function u of the flow. So the flow V is divergence free. It is tangential on the inner boundary and also on the outer boundary, but since it is at least tangential on the inner boundary, the flow V has a stream function u. So there is a function u whose orthogonal gradient is equal to V. And this function u is unique up to additive constants. And since v is tangential on the boundary, so the function u is constant on both connected components of the boundary. So u is equal to some constant c on the inner boundary here. And up to, let's say, an additive constant, we can assume without loss of generality that u is equal to 0 on the outer boundary. So actually, the inner boundary and the outer boundary of the domain are streamlines of the flow. So the stream function is constant along these streamlines. So now I claim that any streamline intersects any trajectory capital sigma of the gradient. So the trajectories capital sigmas are the trajectories of these families of ODEs. So little sigma dot equals to gradient u of sigma of t. So these trajectories, when they meet a streamline, they meet orthogonally by assumption. And okay, so let us consider any trajectory capital sigma starting. So we consider a trajectory like that, capital sigma, starting from a point A, let's say on the outer boundary, just for simplicity. So like in the picture. So this trajectory capital sigma enters the domain. Let's say if we can assume, even if it means changing u into minus u or v into minus v, we can assume that the gradient of u points inwards on the outer boundary. So here, so this is the gradient of u at this point, A. So the gradient of u points inward. So the trajectory capital sigma enters the domain for if we say that sigma of 0 is equal to A, then for small values of t, sigma of t belongs to omega AB. So when t is small, positive and small. And this trajectory sigma, capital sigma, cannot go back. It cannot go back to the it cannot go back to A because actually u is strictly monotone along capital sigma. So this is impossible because u is monotone along sigma. If you look at u of sigma of t, so the derivative of this property is equal to the norm of the gradient of u at the point sigma of t square, and therefore it is positive. So this function u of sigma of t is monotone. So u is monotone along capital sigma. So since u is constant along the outer boundary, so the trajectory capital sigma cannot go back to the outer boundary. So this is impossible. Okay, and also capital sigma cannot make infinitely many turns cannot have an infinite length in omega because u is actually so the derivative of u of sigma of t is actually larger than some positive constant. So and u is bounded in the closed annulus. So therefore, the only possibility and also capital sigma cannot end at an interior point by the implicit function theorem, and therefore capital sigma has to end at some point here, which is on the inner boundary necessarily. So therefore, this implies that C is positive actually. Okay, and also this implies that, and this is true actually for any trajectory capital sigma, even if it starts at an interior point. Okay, now let us look at a streamline capital gamma. So streamline capital gamma, so along the streamline, the function u is constant. So u is constant along capital sigma. And since u has no critical point, and since this streamline cannot make infinitely many loops, it has to be closed. And also this streamline capital gamma has to surround the origin. So any streamline, capital gamma, surrounds the origin in the sense that the connected component, the bounded connected component of the complement of gamma contains the origin. So capital sigma surrounds the origin, and therefore it also surrounds the inner boundary. And this implies by continuity that this capital gamma has to cross capital sigma. So capital gamma cross capital sigma, so intersects capital sigma. And this is true for any gamma and for any sigma. So once we have understood that, as I said, so without loss of generality, we can therefore assume that C is positive. And this, since U is constant along capital sigma, this also implies that U is between 0 and C in omega AB, because each interior streamline meets the trajectory capital sigma, and since U is increasing along capital sigma, then U is strictly between 0 and C in the interior annulus. So now we introduce the vorticity. So we consider the vorticity of the flow. So the curl of the flow, which is a scalar function here in dimension 2. So, and which is also the Laplacian of the stream function U. So this vorticity is also constant along the streamline. So it's a well-known fact, which comes from the Euler equations. This is the only place where we use the Euler equations. So the vorticity is constant, and also by definition, the stream function U is also constant along the streamlines. So therefore, we can write the functional equation between the vorticity and the stream function. So there is therefore a function f such that we have this equation in the whole domain. So this equation is a well-known fact in the Euler equations, but the notations are usually different from by the experts of the Euler equation. So there is the stream function U is called psi, the flow is called U, and the function f is called the vorticity function, is usually called gamma. So here I'm using U and f because I come from let's say from the elliptic and parabolic framework. So we usually call f and U the data. Okay, so it's quite well known to write such an equation in a neighborhood of a point which is not a stagnation point from the implicit function theorem. But the interest of this proof is to write this equation in the whole domain. And this comes from the previous slide. And the function f is cooked up in such a way that this equation is satisfied along a trajectory capital sigma. So we take one trajectory capital sigma, so parameterized by a function little sigma. So we introduce this function theta, which is U of sigma of t. And so this function theta is increasing in some interval 0 capital T. And we introduce the function f, which is in such a way that we have the equation Laplace u plus f of u equals 0 along sigma. So the trajectory capital sigma, which was the blue trajectory of the previous slide. Once we have this equation along capital sigma, since u and Laplace of u are constants along the streamlines, and since each streamline intersects the trajectory capital sigma, therefore we have this equation Laplace u plus f of u equals 0 in the whole domain. Okay? And here, this function f is of class C1. F is of class C1 because this is where we use the fact that the flow was of class C2. So the flow is of class C2, U is therefore of class C3, and by the chain rule, the function f is of class C1. So therefore, it is at ellipsis continuous, and this is where this plays a role because we use now the following result of Boyan-Sirakov. So we can view so we can use this following result. So we have a solution U of a semilinear elliptic equation, which is equal to 0 on the outer boundary and equal to some constant c positive on the inner boundary, and u is strictly between 0 and c in the domain. So here this result holds in any dimension n actually for a function f which is Lipschitz continuous. And once we have this situation, this assumption, then u is radially symmetric and decreasing with respect to the norm of x. So this equation is similar to so this result is similar for those who are familiar with the famous result of Guidast-Nirenberg, the radial symmetry result of Guidast-Nirenberg, which was for, let's say, for balls, for positive solutions in balls, which are equal to 0 on the boundary. So here we have an annulus. So if we have a solution in an annulus which is equal to 0 on both connected components, then the result of Guidast-Nirenberg implies some monotonicity, but on the, let's say, for radius larger than the half radius. But in general, the solutions are not radially symmetric when we have both Dirichlet boundary conditions on both boundaries. So here we have two different values on the boundaries, and u is strictly between the different values, and therefore we can apply the method of moving planes of Alexandrov and Serin, and used also by Guidast-Nirenberg, to show the monotonicity of the function in any direction. Okay, and therefore the radial symmetry of the function u. So we can use this result to say that the function u is, the stream function u is radially symmetric, and therefore the flow v, which is the orthogonal gradient of u, is a circular flow. Okay, so how much time left do I have? 8 minutes.
So 45, 5 minutes.
Sorry?
More or less 5 minutes.
Okay, 5 minutes. Okay, so I'm going to be very fast on just one result in the case of so non-regular annuli. So let me first consider the case of an exterior domain.
You have more than 5 minutes actually. I'm sorry, almost 10 minutes.
Okay. Okay. So let me consider the case of an exterior domain. So the complement of a disk. Okay, so we consider a flow V, which is still tangential on the boundary. So now there is only one connecting component on the boundary. So this is the inner cycle CA of radius A. We assume that the flow has no excitation point in the strong sense. We assume that the infimum of the norm of the flow is strictly positive in the domain omega A infinity. And we also assume a behavior of the flow. We assume a condition on the radial component of the flow at infinity. So we assume that it goes to 0 fast enough, so little o of 1 over the norm of x when the norm of x goes to infinity. So this is the radial component of the flow. Then the conclusion is that the flow is still a circular flow. So the same conclusion as before, but now in the whole exterior domain. So which means that the streamlines are all concentric cycles. And this also means that the stream function u is radially symmetric. So these results can be viewed as Liouville type results for the stream function u. And let me point out that the flow is not assumed to be bounded here. And there are many examples of unbounded circular flows without any stagnation point. Okay, so there are counterexamples without this condition. Even if we do not know if this condition is somehow optimal, we do not know if the growth assumption at infinity is optimal, but we can see that without it, in general, the conclusion does not hold. Okay, I don't have so much time to discuss this counterexample. I would like to go on let's say some elements of the proof. So the proofs share some, this proof shares some common features with the previous one. So we introduce the stream function u. We consider a trajectory of the gradient flow starting from a point on the inner boundary. And we can show that this trajectory capital sigma goes to infinity. So this little sigma goes to infinity as t goes to the maximal time interval, t max. And u also goes to infinity along capital sigma. And now with the same argument as before, we can say that, and with a continuity argument, okay, continuation argument, we can say that this, any streamline starting from a point along the trajectory capital sigma, so any streamline C of sigma t surrounds the origin by a continuation argument. And so this is the main technical part here. And therefore, we can also say that all streamlines surround the origin. And therefore, that u is positive in the exterior domain. And also that u converges to infinity at infinity. And we can also say that because of the assumption on the radial component of the flow, we can say that the oscillation of the far streamlines, the radial oscillations of the far streamlines goes to 0. So in other words, the far streamlines are very close to cycles. We want to show that they are cycles. What we can say that they are, we can say now that they are close to cycles. We can also write an equation, the same type of elliptic equation as before for some C1 function f. So the fact that f is C1 also plays a role because we apply, when we apply the moving plane method, we compare the function u with some reflection of itself, and we apply maximum principle for the difference. And the fact that f is Lipschitz continuous implies that the 0th order coefficient of the equation satisfied by the difference is bounded. And this is somehow an optimal condition to apply the maximum principle to make the proof work. And so we apply this this method of moving planes in some approximated domains which look like regular annuli, but not exactly annuli, because we don't know that the far streamlines are cycles, but they are close to cycles. We apply this method of moving planes in some approximated domain up to some parameter epsilon, and then we use a limiting argument to show that the function u is radially symmetric. So this part is quite technical, but this is how the proof works, roughly speaking. So we also have further results in punctured disk with some conditions when at the origin, and also further results in the punctured plane. But I don't have time to talk about that. I would like to mention one serine type result. So another class of result, which is the case when we do not. So now the domain omega is free. We do not know what it is. We take any so omega, which is of class C2, simply connected, bounded domain of R2. And we assume that the flow is tangential on the boundary. And we also assume this additional condition that the norm of V is constant along the boundary. So this is an additional condition. So, and we also assume that the flow has a unique stagnation point in the domain. Okay, once we have this assumption, so we can still introduce the stream function u of the flow. And therefore, the stream function u has only one critical point, which has to be an interior point, because actually the stream function u is constant along the boundary, and it also has a constant gradient, constant normal derivative along the boundary. So the stream function u has a constant normal derivative along a constant along the boundary. And therefore, we have another determined problem for the function u. And if the function f, if the vorticity function f were Lipschitz continuous in the whole range of u, then we could apply directly the results of the serine type results to conclude that the domain is the disk. So here the function f, the vorticity function f, may not be Lipschitz continuous in a neighborhood of the maximal value of u, and it is not in general. We can find counterexamples, but we apply somehow an approximated serine type argument to conclude that the domain is still invariant by rotation. So the domain is the ball up to shift, let's say, centered at the origin, and the only stagnation point of the flow is the center of the disk, and the flow is a circular flow. So I think I have to stop here. So there are other results in the whole plane. I didn't have time to mention them, but I think I have to stop here. And thank you for your attention.